A B tree is a specialized M-way tree commonly used for efficient disk access. In a B tree of order M, each node can contain a maximum of m-1 keys and have up to m children. Its primary advantage lies in its ability to store a large number of keys within a single node, including large key values while maintaining a relatively small tree height. A B tree of order M contains all the properties of M-way tree. In addition, it contains the following properties. Each node in a B tree contains at most m children. Every node in a B tree except the root node and the leaf node contain at least m by 2 children. The root nodes must have at least 2 nodes. All the leaf nodes must be at the same level. It is not necessary that all the nodes contain the same number of children, but each node must have m by 2 number of nodes. A B tree of order 4 is shown here. While performing some operations on B tree, any property of B tree may violate, such as number of minimum children a node can have. To maintain the properties of B tree, the tree may split or join. Let's see the operations performed on the B tree. First one, searching. Searching in B tree is similar to that in binary search tree. For example, if we search an item 49 in the following B tree, the process will be like this. Compare item 49 with root node 78. Since 49 is less than 78, hence move to its left subtree. Since 40 is less than 49 and 49 is less than 56, traverse the right subtree of 40. 49 is greater than 45, move to the right. Compare 49, match found. Now return. Searching in a B tree depends on the height of the tree. The search algorithm takes big O of log n time to search any element in a B tree. Next option, insertion. Insertion are done at leaf node level. The algorithm needs to be followed in order to insert an item into a B tree. Let's see the algorithm. Traverse the B tree in order to find the appropriate leaf node at which the node can be inserted. If the leaf node contains less than m-1 keys, then insert the element in the increasing order. Else, if the leaf node contains m-1 keys, then follow the steps. Insert the new element in increasing order of elements. Split the node into two nodes at the median. Push the median element up to its parent node. If the parent node also contains m-1 number of keys, then split it too by following the sum steps. Insert the node 8 into the B tree of order 5 as shown here. 8 will be inserted to the right of 5. Therefore, insert 8. The node now contains 5 keys, which is greater than 5 minus 1 is equal to 4 keys. Therefore, split the node from the median, that is 8, and push it up to its parent node as shown here. Now let us see the deletion. Deletion is also performed at the leaf nodes. The node which is to be deleted can be either a leaf node or an internal node. This algorithm needs to be followed in order to delete a node from the B tree. First, locate the leaf node. If there are more than m by 2 keys in the leaf node, then delete the desired key from the node. If the leaf node doesn't contain m by 2 keys, then complete the keys by taking the element from the 8 or left sibling. If the left sibling contains more than m by 2 elements, then push its largest element up to its parent and move to the intervening element down to the node where the key is deleted. If the right sibling contains more than m by 2 elements, then push its smallest element up to the parent and move intervening element down to the node where key is deleted. If neither of the siblings contain more than m by 2 elements, then create a new leaf node by joining two leaf nodes and the intervening element of the parent node. If the parent is left with the less than m by 2 nodes, then apply the above process on the parent too. If the node which is to be deleted is an internal node, then replace the node with its in-order successor or predecessor. Since successor or predecessor will always be on the leaf node, hence the process will be similar as the node is being deleted from the leaf node. Let's see an example. Delete the node 53 from the B tree of order 5. 53 is present in the right child of element 49. Delete it. Now 57 is the only element which is left in the node. The minimum number of elements that must be present in a B tree of order 5 is 2. It is less than that the elements in the left and right subtree are also not sufficient. Therefore, Merge it with the left sibling and intervening element of the parent, that is 49. The final B tree is shown here. Let us see some applications of B tree. B tree is used to index the data and provides fast access to the actual data stored on the disks. The access to value stored in the large database that is stored on a disk is very time consuming process. Searching an unindexed and unsorted database containing n key values needs big of n running time in worst case. However, if we use B tree to index this database, it will be searched in big of log n time in worst case.